I am an engineer, and this is probably not going to be an engineer's perspective, by the way, just to put that out there. For those of you who have heard me speak a few different times, I'm not planning to go into so much of the technical detail as I normally do. I'd like to tell a bit of a story instead. I'm going to move fairly quickly, so you'll need to stay with me. As Dominic said, I am an engineer. I have a civil degree. I have a pavements degree. Believe it or not, I have a teaching degree as well, but we ignore that. It's from a past life. Okay, so here's what I'm going to talk about. So let's get straight into it. I told you I was going to move fast. Here's the issue, as I see it. So physics and engineering have had great success in predicting future outcomes, as in we take known physical law relationships, such as force equals m times a and so on, and we can determine with essentially exact precision the loadings on structures we're not estimating, we're calculating. However, cost estimates are a little bit different. Estimates imply uncertainty, so we represent estimates as a probability distribution to represent essentially some sort of risk story, if you like, where there's a range of possible outcomes. The problem or the question is this the true risk story? So when we have an estimate, does that distribution represent the true risk story or not? And as we've heard from Marion and others, it's often not, because we see overruns or underruns. So that mustn't be the true story. The answer is something else. What is it? And how do we get there? So as we heard a little bit, the phenomenon of cost overruns is well documented. There's no shortage of explanations. However, it should be pointed out, as some have articulated, Professor Love, for example, there is no universally accepted theory as to what causes cost overruns. And there's those really two explanations there, as you can see. And look, it's not easy. Not easy to estimate. It's difficult to estimate, particularly about the future. Future ain't what it used to be. Apologies to the economists in the room. I'm sorry. Sure, some smiles there. And look, even Professor Frink can't quite get it right either. So, yeah, if he can't get it right, what hope for the rest of us? Hypothetically, if it was known or is known that a project will be constructed exactly as designed, then in theory, hypothetically, supposedly, we could calculate all these quantities and we could have an estimate. It wouldn't be an estimate, it would be a calculation with exact precision. However, that's not what happens, as we know. Site conditions, weather, geotechnical issues and so on mean that what is moved and placed, the productivity rates and so on, they all vary from what was assumed in the estimate to what is actually done. And as Pedro was pointing out as well, what is actually constructed may be different to what was originally designed as well. And some of us have probably seen this chart here, which was floating around for a little while, the supposedly ideal project, and ideal is in italics there, where the final cost is what you estimate it to be in the first place. Contingency gets tighter and tighter as the project goes on. Of course, that's not what happens in reality. It's something closer to this, where as we go along, the contingency through various phases does get tighter and tighter, but then we actually start constructing and all hell breaks loose and something else completely happens and project costs go up. There's plenty of studies out there telling us that cost overruns are an endemic problem, systematic. However, there is other literature out there that suggests that, hang on, it's not just overruns. Overruns are a problem, but underruns happen as well. So I've done a little bit of work as well. I can't share those results, unfortunately, but what I will share, so this is for a sample set that I had, I will say that overruns are an issue as well. My issue is if we remember that chart right at the beginning, the variability. So very little's coming in on budget. It's either way over or way under. The standard deviation is very high. It's not giving a lot of confidence. So when we see an estimate, my view is I don't know if it's going over or under, and by how much, and it could be a lot. And that's a real issue. Underruns are a problem for a funding entity as much as overruns, perhaps even more of an issue, because it means we're locking away capital that we could put to other use. But so that's the problem with underruns. The issue with uncertainty to begin with, if we don't know if it's going over or under, is if we're trying to rank projects by some sort of metric, benefit cost ratio or so on, we don't have the confidence to be able to do that. So we've got a project for $1 billion, for example, with a benefit cost ratio of 1. If it costs $500 million, that benefit cost ratio is 2. If it costs $2 billion, well, the benefit cost ratio is 0.5. That's a large difference. So, and if we don't know what's going to happen, then we're in a pretty difficult position as a decision maker, knowing which project we should proceed with. Humans are different to animals in some respects. We're more intelligent, supposedly. Quick poll, hand up who thinks intelligence is an asset? Who thinks it's a liability? Some people. My question is this, look, if evolution is driving change, not necessarily towards the ultimate outcome, it's random. But if intelligence was such an asset or such a great thing, I mean, surely your dog would be sitting at home now doing some calculus. The frogs in your backyard, they would have launched their own space program by now, but they haven't. So is intelligence really an asset? I can answer that question. I'm just putting it out there. Perhaps it's not as great as what we think it is. Or maybe it is. Maybe it's the ultimate asset. What is clear, though, is that we're riddled with biases. Okay? We lie to ourselves and others. We all cheat a little bit here and there. Some people take in a few pens here and there. Some people do bigger things. We're very fallible. Very fallible. Nassim Taleb calls this the triplet of opacity. So we think we know what's going on in a world that's perhaps much more complicated than what it actually, or what we think it is. We invent stories to tell us what happened, explain what happened, even if it's true or not. And we tend to put a lot of value on factual information, whether it's true or not. And we draw conclusions perhaps erroneously. So here's an example. Imagine you're a turkey for a moment. And we can apply this to pretty much everything. So I'm 22. So I'm 22 years old. And so I've been alive for about 7,000 days or 8,000 days or so on. Just because I haven't died in any one day doesn't mean I'm immortal. Okay? We have to be careful how we extrapolate information. All right, let's go through a couple of quick examples. First example, it's a very easy one, so when you know the answer, just shout it out. Okay?
2. Well, none.
Moses didn't take any animals of the ark, it was Noah. Another quick example, again, fairly easy one. Shout it out when you know the answer.
5 cents. Oh, sorry. $1.05. Oh, yes, no, that's right.
Yeah, 5
cents.
All right, so that was a little bit tricky. It is 5 cents. It's not 10 cents as most people tend to blurt out. We do have a lot of bad habits. Sorry, if I just go back. So it is 5 cents. So often the instinctive response is 10 cents. But if the ball was 10 cents, then the bat would have to be $1.10, so it's a total of $1.20, not a total of $1.10, so it has to be 5 cents. People actually feel a lot better if they know that answers to, Moses took 2 or 10 cents rather than 5. People feel better about themselves if they know or think that this is an uncontrollable rational response or an instinctive response. That's another way we make ourselves more comfortable. All right? So it's just something to be aware of as humans. If we go back a little bit though, Aristotle's views really shaped thought for a long, long time. This Aristotelian view that nature was driven by purpose, reason and observation was all that was required, didn't leave a lot of room for experimentation. That changed a little bit, or started to change certainly into the Renaissance, where we had Galileo, followed by Newton, and his contemporaries, Halley and Boyle and so on, who or particularly Newton, once he had formulated his laws of motion, then that sort of, there was this then growing belief that, the universe or the world is mechanical in nature, and we just need to understand all these physical laws and relationships. And that grew then further during the Enlightenment, where people thought, yes, the universe is essentially deterministic. If we know enough about its past state and its future state, we can predict with exact precision going forward. And it was Laplace who took that to its extreme, when we talk about, I don't know if anyone's heard of Laplace's demon. Now, those of you who have did some maths at uni, we're not talking about the Laplace transform here. I know I struggle with it. We're not talking about that's not the demon we're talking about. We're talking about a different type of demon, a demon which is some hypothetical being who's so well informed with enough processing power can predict the whole history of the universe and its future. All right. But that's destroyed by a number of principles. So second law of thermodynamics, so information is not conserved but lost. Uncertainty principle in quantum mechanics, and also chaos theory. So I won't go into that, but chaos theory, yeah, I guess most people are familiar with the sort of this part of chaos theory says, very small changes in initial conditions will result in huge snowballs effect, and because of other issues such as uncertainty principle, we can't know the exact starting position. All right, so what am I going on about here?
Good question.
You might ask. Yeah. The reason I'm doing this is to sort of try and explain that there's a tendency for people to, when we're thinking about cost and risk, to believe that if we understand every single aspect or element of a system, if we dig deeper and deeper and deeper, we can get to this point that here we can get the exact answer, calculate precisely. The question is, can we actually do that? So when we're talking about a model, a cost model, a risk model, an integrated model, we're not talking about some sort of replica of reality, like a model car where you've got a stationary object and you just have to replicate it exactly. We're talking about some sort of system. We've got, think about what's happening physically. There's guys running around, there's materials coming in that have to be moved and placed, there's all sorts of plant moving around, people are making thousands of decisions a day, or collectively. That is what's happening on the project. So getting yourself caught up and wondering, okay, is my labour rate $69 or is it $68.50? That's not our issue here, okay? But that's what I tend to see, I should mention, so I review projects for the Commonwealth, so I see a lot of cost models, a lot of risk models, and this is the sense I'm getting that there tends to be people thinking if they just get to the exact level of detail, the ultimate level of detail, we can work out what the cost of the project is without and just ignoring all those things that are going to go wrong. Okay, so that's where I was sort of going with this. So sometimes adding detail is not necessarily helpful. So a quick example, let's take a road. So we can just a road of some sort of length, doesn't matter how long. We can make a really rough estimate of that, but for decision-making purposes, we need to have some sort of a fairly calibrated answer. We can't just say, the cost is between $0 and $1 billion. That doesn't help anyone. How do we choose? How do we know if that's something we should invest in? We need a tighter answer. So we can narrow our bounds, but then we become necessarily less certain about how accurate they are. So, for example, we say, we think it's $100 million. Could be 50, could be $200 million. That's an accurate answer in that the project is likely to fit within that bound, but it's not very well calibrated. We can, and we may be 99% certain about that. We can narrow that down and say, maybe it's between 80 and 130, but we're now less certain because it could fall out of those bounds. So what do we do? The usual response is to start disaggregating those items. So, okay, we've got a road, let's disaggregate. Let's look at earthworks, drainage, pavements, and so on, and dig down because we can get a closer range on each of those. But we need to then start thinking, yes, we can never get to the point where we're 100% certain on anything, and we have the curse of dimensionality and various other things. Some people in this room can probably explain a little bit more detail when we're talking about a model that's mathematically overdetermined. But just because we're adding detail doesn't mean we're getting more correct, or our whole entire assumption set is more correct. So, for example, if we have 10 elements and we're 60% certain in each of those, then our entire assumption set, the chance that our entire assumption set is correct is 0.6%. But as we add more detail, you can see now we've got 50 items and we're 85% correct, but we're actually less certain our entire assumption set is correct, and so on as we go. So we can even sort of calculate that, you know, how certain do we need to be on our ranges to be sure that we continue in the same way that our entire assumption set is sort of the same value. So again, the lesson is, let's not get caught up on the minor detail. What's actually happening? What's happening in this system? What are the state variables? How are they interacting? Again, labour rate. Yeah, it's important for first principles estimate to understand our quantities and our rates and our materials and so on. But think about the interactions. All right, so where does this lead us? We had another slide by Pedram, which showed all the different possible methodologies. Here's a few here. There's no shortage of methodologies out there. And so the department recommends risk factors wherever practical. We also acknowledge, of course, there's other methodologies that might be more applicable in certain situations. So we've tried to put it out there and say, look, here's different methodologies. You've got a lot of data, maybe a parametric model is best. Pre-tender estimate, you've got a lot of detail. Perhaps there's other methodologies that are more appropriate. And internally, there's some work going on, mainly by myself. So we're trying to build a parametric model. I'm collecting past data on past projects, trying to make sure in our escalation model, for example, that our weightings for each of the inputs, labour, plant, bitumen, steel, are as reasonably accurate as we can, so we can have a better escalation model. But the question is, here's my question again, is there a bigger issue at play here? We're working our models, trying to make them better. Are we missing the big picture? So the challenge, as I mentioned before, physics and engineering have had great success in being able to calculate things. But if we're not at that point in terms of estimating, the question is, how do we get there? Can we get there? Perhaps is another question. If we can't get there, how confident should we be? Because when we get to the point, or close enough to the point where we are calculating essentially projects, we can take politics out of it. Because at the moment it seems that anyone can make it announceable, because it's kind of like, oh, the project, you said it was $1 billion, it was $2 billion. Yeah, okay. We knew that all along. But once that's gone, if that's not happening, then there's accountability. And we can remove that layer. So that's why it's so important to keep working on this. So where do we go? I was really pleased for that when Dominic invited me to come here, because I don't have all the answers. And what I'm putting out there is we all have different incentives, and that's okay. So in academia, sometimes there might be a tendency to look at a problem for its problem's sake, for the intellectual challenge perhaps, without thinking about the practical application. In industry, consultants, of course, there's concerns around IP, and that's okay. That's partly what capitalism is built on, is that, rewards flow to those who work towards it, and there needs to be those copyright rules and so on. But there's a tendency to want to hold that, of course, because that gives you an advantage. That's fine, but we need to be aware of that. In government, there's that's not what the incentives are in government, but there's different incentives. But how do we join that up? Okay, so I'm here. And I want to put it out there to say, I want to work with academia, with industry, to work out what we can do in government to keep improving here. So I'm saying I don't have the answers. I've got my contact details, so you can all contact me and work out how we can do this together. I mean, we don't have the answers today. Can't figure that out right now. But that was why I was so pleased to come today. So we definitely need a joined up approach. So I want everyone to go away and think about that. How can we all help each other here? And that's really where I want to leave what I want to talk about anyway. Please let's work out how we can create a joined up approach to solve this issue or solve this problem.